International Day for Women and Girls in Science, which was hosted by American Space Valencia, which is sort of an American diplomatic outpost on your campus. It's sort of surprising that exists, but it does. The long hand of the United States reaches even into the universe. All right, So one thing I want to say is, so the reason I am at the University Polytechnic Valencia is because I have what's called a Fulbright Fellowship. So the Fulbright program is run by the United States Department of State, and it brings scholars from the United States out internationally, but it also brings students from Spain and other countries to the United States. So it is a program that you could look into. There are opportunities to do research or study sponsored by the U.S. Department of State in the U.S. So if you're interested in that, it's a way to get funding, to have it's not as, sort of like Erasmus, right? A little like Erasmus, but in the States. So anyway, so look into it if you're interested. Please get in touch with me if you have any questions. Let me say just a few things. So again, I am at American University. That is in Washington, D.C. So there's the White House. That's about 5 kilometers from the White House. We're looking forward to an exciting year in Washington, D.C. It's always exciting. So in the United States, there's both public, just like here, there's public and private universities. This is a private university, although maybe in the U.S. that's a little different than here. Like Harvard's private, right? So anyway, I don't know. So we're private in my department. So I'm a physics professor. My department is undergraduate only. So I do teach primarily bachelor students, right, for most of my time. Most of my teaching is that. Also in the United States, if you're a physics professor, you end up teaching a lot of other majors because everyone is required to take science classes, even if you're majoring in political science or art. So I teach a lot of students from across different disciplines. Okay, just so you sort of have a little bit about who I am. So I did my bachelor degree at a school called Duke University, and I actually have a dual degree in physics and English. So I like talking. I have a lot of words. I did my PhD at University of Texas at Austin in the 90s. And at that point, particle physics was what I was doing. I had been sort of raised to believe that the most important question in the universe is, what are we all made of? I now no longer think that reducing everything to particles is the most interesting questions. I'm more interested in emergent phenomena, even in the quantum systems. But anyway, so I moved away from that because right in the 90s, and I'll get to this later, was right when quantum information theory was suddenly exploding. A guy, and I'll talk about this, a person figured out that if you could make a quantum computer, you could efficiently factor large prime numbers. And then suddenly, every government in the world started funding research in quantum information and quantum computers. And so it was the subject was new. There were many easy problems that hadn't been solved yet. It's sort of like if you were doing computer science in the 60s, right? Like nobody'd written any computer programs hardly. So every program you wrote was the first program to do something. Every algorithm was new. So that's what it was like in the 90s and early 2000s. So eventually, I was a postdoc after my PhD. I was at Rice University, which is in Houston. And then I moved to American University, where I became an assistant professor. And then in studying quantum information theory, and I'll talk a little bit about this. So one of the main, so you actually have to, the computers are built out of silicon chips. They used to be built out of vacuum tubes. Well, so we are still debating what is going to be the right kind of material to build quantum computers out of. But one of the possibilities is ultra-cold atoms. So I started studying the physics of ultra-cold atoms, the quantum mechanics of ultra-cold atoms, and that's what I study now. That's what I do. Although in all of this, just my true expertise, my secret flame, the thing that burns brighter in me than anyone else, is I understand a lot about symmetry and quantum mechanics. That's the place where my pride lies, right? So, and we all know that pride is a sin that usually ends in tragedy. All right, okay. So just to say one more thing about who I am, the other thing I do, I am director of something called the NASA DC Space Grant. So Washington, D.C. So NASA has in every state and in D.C. and Puerto Rico, NASA gives a block of money to one university in that district, and then we give it out to other higher education in the district, or in our jurisdictions. So we get $900,000 a year, and that's to help undergraduates and graduate students develop workforce skills that will prepare them for careers at NASA, right? And more generally, the aerospace workforce. So this is something, takes about 20% of my time. Next week, at this same time, I will be talking about this. I'll be talking about NASA and how to get involved with NASA, and also just sort of their missions and things like that, next week at the Department of Aerospace Engineering. So, if you're interested. Okay, yeah, so, okay, well that's enough introduction. All right, so, again, the title of my talk was Quantum Technologies, Prepare for Disruption. All right, that's a little cheesy, and really this is still a question. So maybe we'll open this with this question: is right now the quantum technology industry is growing rapidly. They say it's about a $400 million industry right now, and by 2030 it could be up to $3 billion. Right? So they say it's growing rapidly. Maybe, right? So why are people putting so much money into this? I have colleagues who are professors who are leaving their jobs to start companies, right? Being a professor is a very secure job. Why would anyone do that, right? So I'll try to at least, besides providing a technical, I'll try to provide at least a little bit of the cultural background of this too. Okay, so, but the critical thing is first off, quantum, like what do we even mean by quantum? I don't know what you know about quantum mechanics, so let's start at the beginning. So the physical laws, we have Newton's laws. They're very good up here at this scale. If we go to things that are very large and very fast, we use relativity, Einstein's special and general relativity. But if we want to study things that are very cold, very slow, and very small, we have a different theory, quantum mechanics. People who studied, in the early 20th century, there were some mysteries about how atoms emitted light and about how hot objects emitted radiation, and these kinds of mysteries led us to a theory of quantum mechanics. We still don't really have a complete understanding of how quantum goes into classical and how classical goes into relativistic. In some sense, that's still one of the big questions of physics, but what I'm going to talk about is quantum. And so, of course, the most fundamental thing is that all stuff is made of atoms, and atoms follow the rules of quantum mechanics, so basically all technology is quantum technology, right? I mean, if every technology is made out of atoms, now there are certain technologies that you may be familiar with that are sort of the technologies the technologies we associate with the information revolution and sort of the transformation of our economy in the last 50 years, computer chips, lasers, semiconductors, to some degree LCDs and LEDs, right? All of these are silicon-based technologies in which the rules that govern them and how they were invented relied on quantum mechanics. Similarly, nuclear technology, that relied on us understanding quantum mechanics. Right now, if you've heard of nanotechnology, there's another whole sort of new wave of technology coming through where the structures that we are interested in are literally at the atomic and molecular scale. And again, those technologies are, in some sense, quantum technologies. It requires quantum mechanics to manufacture, to measure, and to implement those technologies. But that's not what I'm talking about. Okay, that's not really what I'm talking about. Now, you've probably seen, what I'm talking about is you've probably seen this graph or some version of this graph before. So we have years on the x-axis, and we have, let's see, number of peak speed. I think this is measured in the number of either operations at first and then flips, like bit flips in the blue part. And that is in a scale that goes from 10 to the minus 1, so in other words, a tenth of an operation per second, all the way up to 10 to the 17. So 100,000 million operations per second. So this is a logarithmic chart. This is a logarithmic scale. And you see that it's roughly linear. But if a logarithmic graph is linear, what that means is it's really exponential, right? So this is a graph that shows that computational power is exponentially growing. This is known as Moore's law. It's not really a law, right? It's just something that happens to look like it works, right? That if we sort of take this chart, we can see there's an exponential growth in computing power. And this only goes up to 2020, but you get the picture. What we are afraid of, I don't know why we're afraid, but I'll call it fear, is that this thing is going to flatten, right? And people have been predicting that it's going to flatten for a long time. And the reason people think is most of this speed up has come because we have made chips, we have made the transistors on chips, the integrated circuits on chips, smaller and smaller and smaller. At some point, the transistor we need will be smaller than a molecule or smaller than an atom in order to keep this exponential growing, and that's not possible, right? So silicon-based computational power is going to end at some point. Now, there are clever electrical engineers and computer engineers who are finding ways to make, right, most of our chips are still two-dimensional. What if we start making our chips three-dimensional? Or what if we find a really clever way to have this part of the chip talk to that part of the chip? So we probably, without even making a new kind of transistor, still have some more exponential growth in our future, right? There are still clever technologists who are going to make this go better. But at some point, we're going to reach a limit to where we cannot make the things any smaller, any more powerful without changing the underlying material we are running, right? We're going to be at the quantum scale when we're doing the computations. So this observation was made by a physicist named Richard Feynman, maybe back in the 80s. And then somewhere in the 90s, people started really taking it seriously and started inventing algorithms. And so I'm going to go into one of these later, but just to say this out loud, these are sort of the 4 domains where it has been realized that we're going to reach a classical limit with our computers, so we need to start thinking about how we can do these kinds of technologies with quantum systems if we're going to maintain our growth and capacity. Today, I'm going to talk a little bit later about quantum communication, maybe a tiny bit about quantum computing. So we'll save that for a second. Quantum sensing, that is where we use the quantum properties of matter to make ultra-precise measurements. Measurements that are not possible with classical measuring devices. I have a colleague, for example, who works at what's called the Laser Interferometer Gravitational Wave Observatory, or LIGO. They're the big observatory. They're huge. They've got a big one in Louisiana in the U.S., a big one in Washington State in the U.S., little ones in India and Italy, and also they're working on a space-based one that measures gravitational waves that come in when black holes collide with each other, right? And they started making these measurements. The detector, they turned it on in the early 90s. It didn't measure anything. They upgraded it. They started measuring them in 2015. They've turned it off, and they're going to start measuring again, but this time they're going to use quantum sensing. They're going to use quantum light to make their interferometer even more powerful. And so we're excited for that to happen. So quantum sensing. Other applications. You want to measure gravitational fields very, very precisely, because then you can detect what is under the Earth. You can detect whether there's a natural gas deposit or an oil deposit or fresh water, or I got a friend who has a grant to sense underground cavities, because if there are underground cavities, it could be where agents are doing nuclear tests, right? And we want to be able to detect these underground nuclear tests more precisely. Another application, quantum sensing. You want to be able to do really precise gyroscopes, right? So gyroscopes telling you what direction you're moving. If you combine a precise gyroscope with a precise enough map, you don't have to use GPS. You could steer your food bomb without having to have GPS tell you where it is. I don't really mean food bomb. I mean bomb. Right, but right. So this, the U.S. Department of Defense funds a lot of work on quantum sensing to make ultra-precise gyroscopes, so we can deliver missiles without having to have them have any antennas. Okay, quantum simulation, another application, a lot of promise, perhaps a little bit of over-promise. One of the hardest problems computationally that we have that is limiting medicine is that we know that complicated drug molecules, typically some mixture of proteins and all sorts of stuff, they have really complicated shapes. And their precise shape tells you whether it interacts with the cell and turns it on or off, or turns on or off the RNA cycle in the cell. But it really depends very precisely on these molecules, which may have thousands of atoms. That's a really, really hard chemistry problem. And the hope is that we're going to be able to find a way to simulate those molecules with a quantum system that allows us to do those calculations sort of basically like with a quantum abacus, right? So like by moving little atoms around, you would actually be able to do the calculation. So that's another promising one. Or another very hard problem is we'd like to have room temperature superconductors. We'd like to have materials that you can keep at room temperature, current flows with no resistance. Then you can make awesome magnets. You can do all sorts of great stuff, but we don't understand how to design those materials yet. And so in my work with ultra-cold atoms, one of the things we always write in our grant proposals is we're going to do quantum simulators of superconducting materials to try to solve this great technological mystery. So, okay. In quantum computing, again, sort of the introduction, we just want to make computers that are going to not be limited by the size of the chips and maybe have different kinds of power. So, okay, so just to say this, top 5 qubits. So, yes?
I have a question about those big problems that you are telling us. So, it is so difficult to create a model of these molecules that you want to iterate with a quantum computer in order to accomplish that simulation.
Yes. Yeah, and I'll sort of try to explain why it could work better in a second. Yeah, right. And so I'll try to explain why we think it could be more efficient. I mean, again, typically those kinds of problems scale exponentially with the number of atoms. Right, so that if you add one more, so that's bad, right? So we're looking for new quantum algorithms, so instead of scaling exponentially, maybe it scales like a polynomial, right? And so that's the advantage we're looking for in a quantum system. So I'm going to mostly talk about theory, but just for those of you who are interested in the actual technology of it, there are 5, so a qubit is going to be the working bit of the quantum system. We'll say more about that in a second. But the top 5 possibilities are what's called quantum optics. So using the quantum properties of single photons in lasers or superpositions of lasers. So that's just a picture of a complicated quantum optic or a complicated optics table. And so that's the one. This is the one that already got the Nobel Prize for Zeilinger, for example. This is the work he's doing. So they have used this system to test some of the foundations of quantum information theory. But the most promising commercially are called superconducting qubits. So these are the ones that are most like little circuits, except the circuit elements themselves are so small you see their quantum properties. But a superconducting qubit is basically like a small LCR circuit. Have any of you studied like LCR circuits with an inductor, a capacitor, and a resistor? Imagine you make that so small that it works like a quantum device. That's what those are. That is what IBM now has a computer with 500 superconducting qubits, and that's the biggest functional quantum computer in the world. That is not enough to solve hard problems yet. It is still barely enough to play, tic-tac-toe, right? It's not, so it's more still they're doing research. It's not yet practical. Although you can sign up, you can do a grant application, and you can submit jobs to it. You're allowed to submit jobs to it. I think they have 128 one that is open to the public if you just do a competitive grant application. So that's the most promising. A lot of people work with what is called trapped ions. So this time you make atoms really cold. You take off one of their electrons so they're charged. You trap them in this oscillating electric field, and then you shoot lasers at them, and you can do some quantum information with that. People don't think it's going to scale very well, but you can at least do some quantum information processing with that. The one I study the most are, instead of ions, you have neutral atoms. And we have figured out, even with neutral atoms, you can use lasers to make patterns of light, and the atoms will sit in these patterns of light, and then if you tune the electric and magnetic fields around them, you can make these little spots interact with each other. And so that's the system I study right now. And that's a rapidly growing field. This is a picture of something called quantum tweezers. These are a bunch of single atoms in quantum tweezers, and we can control their quantum states. And then finally, this is a really cool one, and people study it. They're called nitrogen vacancy centers in diamonds. Okay, so you got a diamond, pure diamond, all carbon in this beautiful crystal array. Nothing's perfect. Sometimes there's a carbon atom. Sometimes instead of a carbon, you have a nitrogen atom stuck in there and a hole next to it. So a nitrogen and a vacancy. Turns out that works like a two-level system, just like a bit, and you can, with lasers, make these solid-state crystals that have these quantum bits inside. So those are called nitrogen vacancy centers, and there's probably 100 people in the world working on those right now. So, okay, so those are the top 5. But again, I haven't even told you what quantum is yet. So why do we think these systems are going to do something exciting? Well, it's because quantum has properties that are different from classical. And these are some of the buzzy words. Entanglement, wave-particle duality, uncertainty principle. Let me tell you at least what a few of these ingredients are. And again, this is very high level. I can go into much more detail, but I think this is the right. Let's see. Please ask questions. I can go on for too long. I won't. The first ingredient is called superposition. So when we have a classical bit, or to distinguish it from a quantum bit, we sometimes call them a C bit. We know every bit is either a 0 or a 1, right? If it's not a 0 or a 1, your computer's broken, right? It's got to be 0 or 1, and they're not supposed to change, right? It's supposed to, if there's a problem, maybe one of these bits can accidentally flip, right? And if you are really doing like machine-level coding, you sometimes have to put in these sort of error correction bits to make sure that, I sent this signal, but I have some sort of trick to make sure there wasn't some sort of mistake made in the communication from this circuit to this circuit. Okay, but those are classical bits. Well, so here's the thing. A quantum bit, and maybe the best way to think about this is, maybe another way to think about this is, instead of either it being a 0 or a 1, a quantum bit is like a vector with 2 entries. So a two-dimensional vector, and each of these numbers, A0 and A1, those are complex numbers that add up to 1. So that means a quantum bit, instead of having 2 states, has an infinite number of possible states. A single bit has an infinite number of states, And these states can be any combination of 0 and 1 at once. One of the first quantum algorithms was this idea is, what if there was a number and you wanted to guess the number? Sounds like a pretty stupid algorithm, right? But so you know you have some number and you want to guess the number. The best algorithm for that is you just start guessing numbers in order, and on average, about halfway through the list of numbers, you get it, right? Like, that's the best possible system, if it's a classical number you're trying to guess. With the quantum algorithm, what you can do is you can guess all the numbers at once, right? You can literally, instead of just plugging in one number at a time, you can plug in all the numbers at once. Now, there's going to be a problem here, is that your quantum computer is going to have uncertainty, and so you're not going to know with certainty for each guess whether you were right or wrong. But on average, instead of working as n over 2 in the number of digits, in other words, being about half the number of possible numbers, it goes like square root of n. And that's a huge advantage. And it all comes down to this notion of superposition, that a quantum bit can be both 0 and 1. And again, to just sort of go a little theoretical here for a second, I don't know what's taught in in classical computing anymore. I've been in the quantum world so long, but this is my impression of classical, right? So say I've got a phrase that I want to quantify, right? So what do? I take these letters and I turn them into ASCII, right? And then these ASCII really correspond to binary strings. And so the famous Shakespearean phrase, et tu, Brute, really comes down to some number, right? In this case, et tu, Brute in ASCII coding has 91 binary digits, right? So that phrase is 91 bits divided by 8. You got the number of bytes. So what? That's like 12 bytes, right? So in the mid-20th century, people like Hartley and Shannon figured out then that really you could quantify information, that it was a consistent mathematical theory to literally quantify information by convert it into bits and count how many digits there were. And so that's where the origin of this comes from, right? And the interpretation then, and again, you can do this with pictures and sound and everything, and their interpretation of this is that, so if I send you this string, the information stored in the string is basically the fact that this is one choice out of 2 to the 91 possible messages with the same length. So this idea is that there's this fundamental connection between probability and the number and information. So this is like classical information theory. Well, so the idea that now we don't have them 0 or 1 requires a whole new framework. So, for example, so if you have a bit, we think of now instead the state of a bit you can represent as a point on a sphere if you know everything about it, and if there's some uncertainty, it's a point inside the sphere. This is called the block sphere, all right? And so this is how you represent one bit as a geometrical object. If you have 2 bits, well, so then you have 4 basis states, right? You have 2 for each one, and you have a coefficient for each of those bases. So you can say, okay, how do I geometrically represent this? Well, so this ends up being a 7-dimensional object. Most of you can't read 7-dimensional objects. I've heard people say this looks like a cat shooting lasers. No, this is 7 dimensions. You just may not be able to understand it. You're so naive. Okay, but anyway, so this picture is very different, and in the end, of course, geometry doesn't help us very much. We actually have to just go on and do linear algebra, right? And so in some sense, if you get tired of linear algebra, don't get into quantum computing, because it's all linear algebra, all the way down. All right, so we have this idea of superposition and this much larger possibility for the kinds of bits there are. Okay. The next 2 ingredients that are central to quantum mechanics is that, and this is sort of let me make sure, how am I doing on time? I don't want to overdo it. We're looking for about 45 minutes to an hour. Okay, yeah, so I've got my qubit, right? My single qubit. So what do these numbers A0 and A1 mean? They are the probability that if I measured that qubit, I would either get 0 or 1. And this is the hard thing about quantum mechanics that philosophers are still debating, but we have pretty good evidence that it works, which says that this state can be both 0 and 1, but if you ever measure it, you only get 0 or 1. So, right, it has an intrinsic nature that is uncertain, and this uncertainty can't be removed, but in the end, in all of these quantum algorithms, you have to measure the quantum bit. Here's a really simple idea, or here's the simplest version of this, is, so electrons are like a spinning object, right? And they have a spin of 1/2. And if you take a beam of electrons or any other ion like this, and you shoot it through a magnet, the magnet will split the up part and the down part. And so if this thing that makes the beam, my preparation device, makes that state, then, and I shot it through here, A0 squared would be up, and A1 squared would be down. As you might think, okay, well, I guess this is the part I'm going to try to convince you, is you might think, okay, well, you just didn't know what it was, and now you do. But in fact, really before the measurement, it really was both. And there's a whole bunch of physics people have done, so and in this analogy you would say spinning with your, spinning around it so that your axis is pointing in the up is plus z, minus z, and that would be, we call that 0, and we call that 1. You can keep doing these experiments, and they've actually done these. So for example, if you shoot this state through, and you block off the ones that go down, and you measure the ones that go up, and then you ask again, up or down, you'll get up again. Once you make the measurement, the quantum system is in a particular state. So here I've made repeated measurements of the same direction. What's weird is if instead I measured the up beam and then I said, okay, how is it spinning in the other direction, in some perpendicular direction, the x direction? You might think, well, it's not at all, but you actually find it splits again. And half of it's going one way and half of it's going the other. Because these states have properties that are not obvious. So spinning up in the z is sort of like half spinning left and half spinning right. And so these are the correlations we actually measure in the lab and tell us that the state of the quantum system, it's not just that we don't know it, but it has intrinsic uncertainty. The universe is fundamentally probabilistic. There are still physicists I meet who disagree with this and hate this. They are a small minority, and they are so skeptical of quantum mechanics that they are always looking for a way to remove uncertainty from the theory. It's really useful to have skeptics like that because they really come up with critical experiments to prove quantum mechanics is wrong, and quantum mechanics always ends up being right. And again, 2 years ago, Anton Zeiliger basically got a Nobel Prize for proving, yet again, quantum mechanics works. These skeptics are so important to prove them wrong. Here's what's even crazier. Say you send it through, you measure spin up in the z direction. Let's say then you measure spin in the x plus direction. Then you measure z again, and it splits again, right? And it splits again. And if you change the order of these things, you get different outcomes. So there's some interrelationship between when you measure the state, it collapses into one observable, and then if you measure something that is complementary to it but not the same, you lose that information. And so anyway, so this is this combination, I know this was a little hand-wavy, this combination of uncertainty and measurement that is so different about quantum mechanics than it is about classical mechanics. Yeah, so that's, yes?
In order to understand better these experiments,
yeah,
the basic thing that, that's what I understand, is that even filtering different results, you can obtain both results
That's exactly right. So here you filter out, you think you filtered out the z minus, you measure the x, and then all of a sudden you get z minus again. So the act of filtering the state changes the state. And that's something that makes quantum mechanics. The other thing that works like this, for the record, is the polarization of light. So, and it's because truly the polarization of light is also at its root a quantum phenomena. I don't know if any of you have ever seen this classic demonstration. You know, polarizing filters. You have polarized like this way and this way. You put them together, no light passes through. But if you stick a third filter through at an angle, suddenly light comes out. Anyway, so this is another manifestation of, in systems which have superposition, your filtering works very differently than in a classical system.
Yes, and how is that? Because light is not composed of atoms, no?
The light?
Yes.
The light is made of photons. And photons act like little quanta of light. Yeah. Okay, good. Okay. One last ingredient, and again, this is such a big subject. I wrote down this 2-qubit, right? So this 2-qubit state. So one thing in a classical system, you could have, so we often call these two parts of the state. So the first bit is Alice's bit, and the second bit is Bob's bit. That's just standard information theory going back to the 1930s. We always break our system into two pieces, and we call one piece Alice and one part Bob. So you might think that if you have a 2-qubit state, you could always think about it as Alice's part and Bob's part, and you can write it as like a product of those parts, or some sort of, you can decompose it uniquely. And when you can, that's called a separable pure state. But what we find is that there are states in quantum mechanics that are like this. States where as soon as Alice measures 0, Bob, no matter where he is in the universe, knows 1, my bit's in the state 1. They can be across the room. I mean, I think the largest they've ever done this is 300 kilometers. They've done this test where they have figured out that this kind of quantum correlation, you can make photons, they interact with each other, you send them across through fiber optics all the way to other sides of a country. Austria, again, is where they've done this, I think, the furthest distance. They also do this a lot in Switzerland. They're actually using this in banking transactions in Switzerland, although it's more of a PR thing than necessary. But anyway, the point is you can use this entanglement to make you can store information in quantum systems in a way that is not classical and is more robust. It is truly more robust. So this, again, is a whole subject. This is called the maximally entangled Bell state. This is some famous state that is the state that has the most entanglement, or is one of the states that has the most entanglement for the 2-qubit state. And when you read about quantum technology, one of the first steps they're always trying to do is to make a bunch of entangled qubits, because that is like the resource for the computation. So you have to have a physical mechanism that makes a whole bunch of entangled qubits, and then you do your operation based on that. Okay, so, yes?
How do you actually entangle qubits?
Yeah.
Fundamentally, how do you do that?
So, okay, it depends on the kind of qubit. So, for example, in optics, there's something called a nonlinear crystal, where if you shoot in one laser, 2 lasers come out, and the photons in those 2 lasers, it ends up being that there's a nonlinear effect between the electric field and the laser beam and the crystal, that it splits into 2 photons that are entangled. Generally, though, whenever you bring any 2 systems next to each other and they interact through quantum mechanics, their states become entangled. Schrödinger was the one who even invented the word entangled, and he was just talking about if you bring quantum systems together and they interact, classically they would feel forces and then they maybe push apart from each other. Quantum mechanically, they may push apart from each other, but they will record the information of that interaction in their entanglement. And so basically, you almost can't stop them from getting entangled, right? Now, the trick is you want to do it in a way that's reliable and where you know what the entangled state is. For superconducting qubits, for example, that really popular one, you can use a microwave laser to make a coherent excitation of 2 different qubits that drives them to entangled state. And typically for the ions, you can do that by shooting a laser that hits 2 of them at the same time and makes them entangle. In my subject of neutral atoms, one of the coolest ways is if you do it right, you can just shake the trap. And if you shake the trap just right, and there's a little bit of interaction between them, you can control the entanglement that way. So, but, I mean, again, so what's critical to all of this stuff is we need to have control of single quantum systems. This was something, so I got my PhD in 2001. When I started my PhD in 1995, my PhD advisor said, we will never control a single quantum system. And by 2001, there was a Nobel Prize for it, right? So you do have to have incredibly precise lasers, or whatever the technology you do has to be incredibly precise. You typically have to have them really cold, right? Otherwise, any sort of noise will break the entanglement, any sort of classical noise. So yeah, so we know how to do this. I mean, you can still get a paper in a very good journal for measuring entanglement in a new quantum system. So it's still lively. It's still a lively field, but we have a lot of things we know how to do. So for the last part of my talk, I'm just going to give an example of one of the killer applications. And again, this is the application that is what made the National Security Agency in the United States start funding PhD programs in quantum information theory. This is the application that got Europe to start. And I would say right now, this is. Yeah, I mean, so Europe, the US, China are competing for quantum supremacy right now, right? So, right, and this is people talk about this as a strategic imperative and a national interest and this kind of stuff, right? And this is the application that makes all that hype happen. So, now some of you just were at an event on cryptography just last week, so some of this will be very, very familiar to you. I'll sort of give you maybe a little bit of a physicist's perspective on it. So again, we've got Alice and Bob. Alice wants to tell Bob something. So just a little bit of terminology. We call that the communication channel. So Alice is going to use a communication channel to interact with Bob. And then to make this into sort of a game, we have to have an adversary, right? And we always name this person Eve. Eve is trying to eavesdrop. That's the word in English. To listen in when you're not supposed to is to eavesdrop. So Eve is trying to intercept the information in the communication channel from Alice to Bob. And again, we could be talking about fiber optics, we could be talking about electric signals, we could be talking about wireless signals. I mean, we could be sending notes across the room on paper, right? All of those are communication channels. One of the breakthroughs in electrical engineering in the mid-20th century was figuring out how to, again, quantify communication channels, how to quantify the capacity of a channel, how to quantify the encoding mechanisms to turn information into a communication channel, how to figure out how to make communication channels robust to noise, right? This is the stuff that was sort of the breakthroughs that happened sort of in the post-World War II era. Sorry, I always think about everything. In my country, we measure a lot of stuff from World War II, but it was a great war for us. Great war. Okay, I was about to try to slip into my Trump impression. Not going to do it. Sorry about that. All right. Yeah. So again, the point is we want to defeat Eve. So Alice is going to encrypt the message and then transmit it. And again, Bob is going to receive and decrypt the message. Okay. So up until the 70s, the 1970s, all encryption schemes were private key encryption, right? So in private key encryption, like literally Alice and Bob agree on a code, and they have to share it, right? And they have to share it in private. I mean, what are some famous examples, right? We agree, I'll use a crazy set of symbols instead of letters, and then you translate it. Or I'll do a letter substitution, where whenever I'm supposed to write a B, I really write a C. All of these sort of basic symbols. Or ASCII, right, is a kind of symbolic transcription, right? You could even do it so that, right, so that the first time you see an E, you use this letter, this symbol, or this number. The second time, it's this number. That's called a one-time pad, where each message has a different code, but you still have to somehow transmit this one-time pad from one person to another, right? Where you all have to share it. and that's the hard part, right? Because you might be on other sides of the world, or one person's in a submarine, right? And you can't get the pad to the person in the submarine. You know, the most famous of these was the Enigma machine. This is the one in World War II the Germans used to encode their messages. And it was a machine that had a sort of mechanical one-time pad built into it. And then it was famously broken by a group of Polish and British mathematicians. Anyway, it's a whole beautiful story. Anyway, so that's private key encryption. And yeah, and in principle, some of these can be very, very hard to break, but they have two weaknesses. First off, you can break the code, but second off, you could somehow intercept, right? They actually captured an early Enigma machine, and so even though they were using new models, the Polish mathematicians were able to sort of figure out how it was going to work, and that's what led to the whole breakthrough. Okay, we want something different. And specifically, right, we want something different, and this was the thing that was, right, in the 90s, when this was first sort of, when quantum communication was first being discussed, this was also when the internet was exploding, right? Like, suddenly we wanted to actually do secure financial transactions on the internet. And I wanted to communicate with Amazon and say, Amazon, I want to buy something, here's my credit card, but I didn't have a one-time pad with Amazon, and I didn't want to have Amazon send it to me. I spent my last sabbatical in Denmark, right? And one of the first things you do when you get your identity card in Denmark is they actually give you a one-time pad, right? And then you literally have to carry a one-time pad around in your wallet so that every single time you want to log in to your bank account or to your tax account, you have to pull out your one-time pad. They've now moved away from that too. What we want is called public key encryption. Amazon just wants to send me a code publicly. Publicly send me a code that somehow can't be broken, right? And so the first one of these that came up is called RSA encryption. I forget who R, S, and A are. I think A was an Adler. This came out in the 70s. It was invented by British spies, and then then other people independently discovered it in the 80s, right? And so here's the idea behind. There's also more sophisticated versions of this, but they all sort of work the same way. So Alice has a message, right? And just think of this message as a really large number. Et tu, Brute was 91 bits, whatever. Maybe she wants to send a photo. That could be megabytes, right? Whatever. But she's got a really large number, zeros, ones. But we can literally think of it as a really big number, like 10,838,000,000, right? We can just think of it as a big number. So she says, I want to send this to you, Bob. Give me a key. Bob then, and there's a prescription for this that I'm not going to go into great detail on, but Bob then generates a key. The key thing is, Bob has to come up with two pretty big prime numbers, and based on those two big prime numbers, he comes up with three other numbers. Two of those he shared. Oh, one of them he keeps. This is some small number that he just makes up, but he sends her one other small number and one huge number, maybe 500 digits. That's that digit n. And then, right, what does Alice do? Alice takes her message, raises it to the eth power, so m times m times m times n, e times, takes the mod by n, right? So just divides by n, calculates the remainder, and that's the number c. So, right, so n is a big number, so if n had 500 digits, c typically has 500 digits also, but it's just the remainder of this other number, right, divided by n. She sends then her message, this number c. Bob takes c to the power of this private number that he's held back, takes its mod by n, and that's the message. That's bonkers, right? That, like, you can just so this is just pure, beautiful number theory. It's actually number theory that's been around, since at least, like, one of the functions you use is called Euler's totient. Well, Euler was a mathematician in, like, the 17th century, right? So most of this number theory has been around such a long time. The idea of turning it into a secret, a public key encryption, that's, of course, really important. So again, the point is, Alice sends a coded message, and again, Bob can send E and N, anybody can hear. Eve can hear those, right? When you send a message through the internet, for example, right, it literally bounces between servers, and satellites, and cell phone towers, right? It's public. Sure, you can encrypt it, but if you're encrypting it, you've got to encrypt it with something like this. The actual numbers that are sent are public. So yeah, so the key, of course, is N. N has got to be a really big number. And that number has got to be so big that it is hard to factor. Now, I'm going to do the same numbers I did for the 12-year-olds. Let's see how you do compared to 12-year-olds. Let's do a prime factoring exercise. And again, I know some of you just did this last week. Okay. First, do we remember what prime numbers are? Yeah, right, so 2, 3, 5, 7, 11. All right, so there, you know, we go on forever. I mean, there's a whole bunch of number theorists. The properties of primes is something that people have been studying since at least the ancient Greeks, right? It's a beautiful subject. People go crazy studying it because it's so temptingly beautiful. It's well known that one of the failure modes of theoretical physicists is right when they get retirement, they start thinking that they're going to that they see the pattern of the prime numbers and the way the forces of the universe work, right? Like literally, like 20% of physicists go bad that way. Okay. 21. What do you got? 3 and 7. Right? We just know that. We just know it's 3 and 7. Right? We know that every number can be factored into primes, and 21 is just 3 and 7. Okay? 187. Okay, how do you even approach this? How did you approach it last week? Those of you who are part of that, what's the first thing you do?
Trying every other prime number.
Yeah, you keep trying every single prime number until you find something. When's the first one that breaks? 2? Does it work?
Nope.
No. 3? No. And again, maybe you know certain tricks. Maybe you can even make these algorithmically. Like you know the last digit's not divisible by 2, so you don't have to do the calculation. You add the digits, that's easier than dividing. You see, oh, if I add the digits together, I get 16, not divisible by 3. Last digit isn't a 5, whatever. You know, there's tricks for these things. And very, very clever tricks. And even if you do this in terms of binary, right, there are people who spent their whole lives trying to figure out what are the tricks to make this thing work shorter. But in this very naive algorithm, how high do you have to test? What's the biggest prime number? Like, how do you know how many steps you have to go through? Yeah, you take the square root. You know it's never, like, if you don't find a prime, by the time you get to the square root, then you know that you're never going to find a prime because you would have already found one on the other side, right? So this simple algorithm, in some sense, scales like the square root of the number, right? Yeah. You have to also, though, of course, know what all those prime numbers are. And again, sort of going through generating this list. I mean, anyway, there's lots of computational complexities. I don't know how you did it. But the point is, right, I didn't get to here, right? Oh, what was 187? Did anybody do it in their head yet? 11 times 17, right? I mean, we know we have memorized 21. We maybe haven't memorized 187. Nobody's memorized this. Prime or not? Is it prime? Who knows? No, I mean, you have to go up. I mean, so again, you have to take the square root of that. That's like, 3,000. You have to at least do all the primes up to 3,000 to get a good handle on this. It turns out this one is 271 times 3631. That would take a long time. Now, again, on a computer, no. Like on a computer, no, but on your head, it would take a while. The point is, though, is that so small number, it's easy. But it turns out the biggest number that's ever been factored, and it took a network of computers to do it, was 250 digits. That's the biggest number that's ever been prime factorized. So if you make a code where the prime number, where the number you send is 500 digits, there's not enough time in history for all the computers ever made to crack that code, even if they were working together since the first computer, ENIAC, in 1947, right? There's just not enough time. All you have to do is go to 500, and you make an unbreakable code, unless you're incredibly unlucky, and somebody just happens to pick like the right number the first time. So, okay. So that's the whole point of public key encryption. And when Peter Shor said, so, what if you could build a quantum computer, then instead of testing all these primes individually, what if you could use superposition and entanglement to test them all at once? To test all of the prime numbers up to that at once. And it turned out you needed to use both superposition and you had to use the entanglement to try to find a way to generate the list sort of prime numbers that you were testing. So we had a very clever scheme, and it turned out then, I mean, so the best systems are so in terms of sort of algorithmic theory, right? The best algorithms for factoring large number are what are called sub-exponential. They are faster, they grow faster with n than any polynomial, but they don't quite grow exponentially. But anyway, these are hard problems. They're literally known as hard problems in terms of algorithmic complexity. Peter Shor said, I can make this something that scales closer to this polynomial with n. So if you can make a quantum computer, if you just make it big enough, you're going to be able to do this, right? And so that was a huge breakthrough. That was a huge breakthrough. The details of it are, and there have been improvements on it, and it's honestly a little bit more than I'm going to do right now, but that's the whole idea. And as soon as he said that, oh, for the record, if you want to see a fun movie that's very dated, but it's sort of fun, there was a movie in the 90s that in the US called Sneakers. It's Robert Redford, and it's about the first quantum computer. It was right after it came out, and we all were hysterical. Anyway, it's a fun movie. River Phoenix and Robert Redford and a whole bunch of American actors who are all dead now. It's great. It's great. You can watch it and laugh. So the point is then, if we could do this, then Shor's algorithm would break RSA encryption. So then, but what was lucky is already somebody else had shown that if you had entanglement and you could share entangled pairs, there was a way to do what's called quantum encryption, where whenever Eve measured your system, if Eve tried to measure your quantum system, because of the measurement problem, she would destroy the communication channel, and you'd instantly know that Eve was eavesdropping, because it would change the state, and it would be detectable. This is called the Broussard-Bennett Protocol from 1984. This was the first idea that, in fact, and it was funny, right? Because as soon as somebody said, oh, you could break classical encryption with a quantum computer, people said, thank goodness you can also make quantum encryption. And this is actually the system that is used right now, I mean, again, mostly for demonstration purposes by some Swedish banks. Not Swedish, Swiss banks, right? They have these clients who want to believe that their money is the most secure thing, and so they only do transactions by quantum encrypted technology. And yeah, so we don't have a way to break this. So, okay, so the point is if we had quantum computers, we would disrupt all the internet transaction economy. Everything would be destroyed immediately. And then we'd have to figure out a way to do it by making quantum channels, not classical channels, between all transactions. That would be a huge infrastructure. You could do it with fiber optics. Again, the most we've ever done is 300 kilometers, I think. But in principle, like a lot of people are out there trying to make what are called quantum repeaters that would take entangled photons in a fiber optic, store it for a second, and then pass it on without measuring it, right? So you can write grant proposals to make those kinds of things. Okay, so the point is if we have quantum encryption, we then find another way to avoid Eve. I think, yeah, so that was just an example of the kinds of the context for quantum communication. Gave a little bit of the review of the other ones, and that's what I got for you today. That's what I got for you today. So, thanks for your attention. Any questions?
I know there is some theories
Of the quantum encryption?
Yes.
I know, I don't know much about that. No, I don't know much about that. I should know about that now that you're saying that. How old are they? Are these new or are they old?
I heard about them 3 years ago, something like this.
Uh-oh, I better look that up. I don't know that. Okay, yeah, okay. Yeah, I mean, I know, clearly the second people started using quantum encryption, other people start trying to figure out how to break quantum encryption. My guess is so the hardest thing about quantum encryption, right, is this idea that whenever Eve measures the system, you automatically destroy the superposition and you choose a particular state. If I know that people have studied what are called non-demolition measurements, so measurements that don't destroy the state. Maybe they found a clever way to do that for a particular technology. Maybe that would be my guess, but I don't know. Okay, I better look into that. Yeah.
I think at the beginning that you were studying with group theory,
Yeah.
and we studied in mathematics for the double degree with computer engineering, and I wanted to know how is group theory related with quantum?
Yeah. So a symmetry. Whenever you have a symmetry, you can, and so for example, it might be like. Just go back to the picture of the block sphere for a second, right? So I've got the block sphere, and this picture's a little bit misleading again because this makes you feel like everything's real and really they're complex numbers. But for example, the constraint you have, you guys go one more back, is right here, right? Is that I have to have that a0 squared plus a1 squared equals 1. I have to have what's called conservation of probability, right? If I have a state, it has to be some probability measuring it in the two states has to add to 1. So that is a structure, a mathematical structure of probability that has a symmetry, right? Like, so I can imagine making transformations that conserve probability, and I can think of the set of all transformations that conserve probability in a qubit, and that's the group SU2, right? And so in other words, anytime you have a mathematical structure with conserved quantities, you can describe that in terms of symmetry, and the mathematics of symmetry is group theory. So, right, so again, when I draw these pictures, a lot of quantum algorithms exploit the symmetries of probability or the symmetries of these states to find clever algorithms, or to or to even like in my particular work, so I have right. So I'm thinking about systems like this, right? And so that system right there, it's a little bit broken. There's a little bit of noise, but this system has what's called D4 symmetry, dihedral symmetry of a square, right? And so that means that every quantum state of this system should have D4 symmetry. And if it breaks D4 symmetry, then I know there's been noise in the system. And I know my symmetry breaking implies some disruption of information. So there's lots and lots of ways. When I was a very young professor, I wrote a grant proposal saying that I was going to revolution everything by doing group theory and quantum information theory. And my referee proposals back said, "You are so dumb. We've been doing this already for 10 years. So I just was naive. So the point is that basically anytime you have math that you want to solve, anytime you have a hard problem and you want to turn calculus into algebra, you use group theory. So anyway, so I mean, group theory is my religion, so I'm proselytizing you like a Bible preacher. Right? Hallelujah! Didn't mean to scare you.
When it comes to quantum communications, if you wanted to communicate through very long distances, like space missions,
Yep.
would quantum communication avoid the time that
Yep.
it would take to communicate?
Okay, so the thing is, you can't avoid the time, because even the quantum encryption protocols, you have a quantum channel, you always have to have a classical channel in parallel. Otherwise, Bob doesn't know enough Bob doesn't know what to measure to know what Alice sent. So this is a great question, because this is something, is people hoped that you could use quantum entanglement to break Einstein's relativity or to send instantaneous messages. But for every protocol, you have to have a quantum channel and still a classical communication channel in parallel. Otherwise, Bob doesn't know how to extract the information from the quantum channel. Yeah, that's a great question though. And I still review probably one paper a year where somebody thinks they figured out a way to do it, and they're always wrong. So, okay, good. Yes?
When you were explaining algorithms that work by generating all the possible scenarios, so I don't understand how that reduces the time complexity, because you still have to test all of them, right?
So that's a great point. So you send it in, you send in all of them, and then the algorithm acts like a measurement device. So the measurement is probabilistic, and so it will say, this is a great question. You have to know what you're measuring. I'm trying to remember the simplest algorithm. I'm trying to think about what the right way to describe this is. I mean, you have to know what to measure. You have to prepare your incoming, your list of all the possibilities in a way such that it is entangled with what's called the control bit. And so it has to be something where if the system probabilistically chooses the right choice, the control bit flips. And so it's not deterministic, and so there is still randomness in it, and that's why it's not a single shot device. You still have to try it multiple times and hope that one of the keys unlocks it, so to speak. One of the numbers is the right one, but but the number of times you have to do it is less than the number of things you're testing. And so I know that's very hand wavy. I'm trying to remember the name of the algorithm that is the simplest one, that was the first person who showed this. I have so by the way, if any of you are interested, this is my email, Harshman @ American.edu. If you send me an email, I'll send you that algorithm and you'll get the picture. Good.
You say that if cannot hear the message because it destroys the channel, but could be that another attack that just destroys all the channels between a communication.
That's right.
So it's not listening, but it's destroying.
Yeah, that's absolutely, and that is a known strategy, is to just jam the communication channels. So so quantum encryption. If you break all the channels, you're not going to have communication. You have to have, if you want quantum encryption, you still have to have one quantum channel, or a quantum channel and a classical channel. That's right. There. Yes.
Before you mentioned that there is already a bank in the world that has this quantum transaction system.
Yeah.
So is it that difficult to change the actual transaction system to make it quantum, because it has already been?
So what you have to have is both Alice and Bob have to have, so you have to make entangled pairs of qubits, then somehow split them up and give Alice some and give Bob some. So right now, the only way to split that entanglement is literally you have to carry some of these from one place to the other. There are schemes out there where we could be able to generate entangled pairs from long distances, right? So that's what we're hoping for. But basically, there has been a little bit of free space quantum communication without fibers, but almost all of the devices have a fiber optics connecting the two things, and they each basically have to have like a low temperature system of photons, or of atoms coupled by photons. So there's some real infrastructure that we would have to put into place. Yeah, yeah. So it's still a very niche, boutique kind of service. It is not financially practical, right? It is a luxury at this point.
Is it like 100% secure, or are there possibly like vulnerabilities?
So we believe that, I mean, as was pointed out, if you break the channel, then no communication takes place. But, and you pointed out, there may be some technology I'm unaware of that can make a non-destructive measurement. I have to look into that because I'm surprised, right?
Now I think I remember that it was that you can know how you measure the first time the cube.
Okay.
Alice codified maybe with 0, 1, and you can know that she used the measure of 0, 1 and not the x1.
Okay. Okay.
So you don't change the measure, the state, so you don't change the message.
I see. Okay, so you know what basis she measured in, but not what state she measured. Maybe? Yeah? Okay. So I would have said the answer was yes. I now have to do a little research.
I have a question on the LSA encryption and how it works.
Yep.
Because you said that Bob has 3 D, E, and M.
Yes.
And D is private.
Yep.
Only Bob knows it. But for the number for the, if you can put the
Yeah, yeah.
the image, please, so I can show it to you. You know that M equals C elevated to D, equals that expression,
Yeah.
but how do you, was it proven that it is the same?
Yes. The critical thing is what, so let's see if I can do this off the top of my head. The first thing Bob does actually, Bob picks 2 numbers, P and Q, and then let me see if I can remember how this goes. Then, so N, is N the totient? Does anybody remember this?
N was P times Q.
Yeah, yeah. Say it again.
P times Q, and P and Q are primes.
Relative primes, and they're also relative primes. And then I believe D is also a relative prime to them. And then E is Euler's totient of, it's Euler's totient of like P minus 1 and Q minus 1. So in other words, the numbers D, E, and N are all, in some sense, D is sort of a free choice, but they're all based already on Bob knowing 2 large relatively prime numbers. And so these are not, and it's really only because people have chosen these very particular values that the algorithm works.
So D, E, and M can't be
They're not arbitrary. That's right. They are. I think 2 of them are determined entirely by P and Q, and 1 of them just has to be relatively prime to P and Q. Yeah. And again, and D can be rather small, and so yeah. So there can be a whole yeah. Yeah. Okay. Great. All right. Well, thanks again. Have a great weekend. Yeah. All right.